Now that we are familiar with Darcy's law of groundwater flow, the next thing to do is to figure out the soil parameter, which is the hydraulic conductivity here. So there is, if you know nothing else, there is always what's called the Hazen's equation or Hazen's correlation, which is simply a very approximate way of saying the hydraulic conductivity of your soil in terms of centimeter per second is approximately d10 square in millimeters. Why is this d10 but not some other diameter? It is because the pore size is controlled more by the smaller grains, because the smaller grains are able to fill the gaps between the larger grains as well. So your pore size is generally related to the small grains. And there is also a more advanced relationship called Kozenik-Harman, which says the intrinsic permeability is controlled by shape, geometry, etc. of pores, but also is proportional to n cube over 1 minus n parentheses squared. So this is where n is the porosity. So yes, there is the much bigger effect of shape and geometry, but this relationship is also useful if you are looking at the same soil at a different porosity, for example. So these are often used for estimating your hydraulic conductivity. But of course, the much better thing is the determination of hydraulic conductivity. So for that we have both laboratory and field tests, and the simplest one is the constant head permeability tests. So in this one, it is very straightforward. You simply make a setup where you apply the principles we have learned so far. So we are going to have this setup which encapsulates your soil sample like this. And you have a constant head reservoir, and also another constant head which is just usually open to the atmosphere. It can also be another reservoir like this, but it makes things more difficult. So another constant head here where you are able to measure, collect and measure volume of water over time. So of course there are other little details you have here. For example, you have to put porous stones on top and bottom. Otherwise you can't keep your soil in place. So the idea here is, and once you have porous stones, now you are probably going to lose some head in there in the porous stones as well, if the soil isn't too impermeable. Then you need to do either of two things. One, you can correct for that by running the same test without the soil, with just the porous stones. So then you will be measuring how much head is lost in the porous stones, which is actually a bit confusing and difficult. So the more common way that people do it in practice is just have piezometer tubes sticking out at two levels. So you end up with this. So that way, what you end up with is you have a delta H here over this length here. So your I then is delta H over this L. And of course you have a known area. So you can directly write the Darcy's equation. Q is Ki, and you can substitute the definition of flux in there as flow rate over area, and then involve time and volume of water. And that's it. It's very straightforward. Then you are able to determine or measure everything other than the hydraulic conductivity here. Of course, then this is K at lab temperature. You need to convert that to K at 20 degrees, which is the standard. So a couple of little details here. Usually, on contrary to what I drew here reflexively, usually flow is applied upwards. Another detail is rigid walls. The flush with several pore volumes of water to a certain saturation. Because if your soil isn't fully saturated, then your K will not only be different, but it will also be variable with degree of saturation. So you have to do this saturated, and the way to do that is you flush a lot of flow in order to flush out any remaining air bubbles, and you have to do this from bottom to top. That's why I said usually flow is applied upwards, because that's the process to saturate it. And then repeated measurements to ensure steady state and also laminar flow. Now, these are basically various assumptions we make here. Actually, with steady state, yeah, we could use Darcy's law for transient problems as well, but the equation, the form of the equation we use here is for the steady state. So we are solving it assuming it is steady state. That's why we have to ensure steady state. Steady state means it doesn't change over time. So what that means is you have to collect some water, measure time, record that, and then again do that, collect some more water, measure time to check if it is the same. Because if it is changing, if the measurement is changing over time, then maybe it is not saturated yet, so you are still getting rid of air bubbles from the system, for example. The way to check for laminar flow is if your hydraulic conductivity, if your unit head loss, hydraulic conductivity is basically the amount of head loss you lose as well, or related to that. So if you determine hydraulic conductivity at different hydraulic gradients and they don't match, they are off significantly, then you might not be having laminar flow there. So then this test is straightforward. It applies the basic principles of 1D flow directly to the problem. But it has one more weakness, and that is if your soil's hydraulic conductivity is very small, very, very small, so small that at the rate it comes out, the outflow is evaporating faster than the rate of flow. So if that happens, now you are unable to measure anything because you can't accumulate water. It's just evaporating, for example. It's evaporating in this container. And if it is that slow, this test will take so long that you don't want to wait that long. So then we apply a different method. Now the idea is similar, but if your soil isn't that conductive, then you might not need it to be that long. So let's draw it like this. And then you get your constant head reservoir here. On the other side, instead of a reservoir, you have a thin tube, thin and very tall tube. Yeah, that's good enough. So this time, and because now you have a very low hydraulic conductivity, the head lost in the porous stones won't matter. They are still there, but this time you don't really need standpipes on the side. So again, you have porous stones here, and you have very low hydraulic conductivity here. Now, this time the idea is you start with a water table up here. You have this much area up here, and this tube has a much smaller area. Now you are not only applying a very large hydraulic gradient to this, but also you are measuring, you are getting a much better measurement with a very thin tube here. You are measuring the amount of volume of water through the tube, through the change of height in this tube. And because the surface area is small, you are also minimizing your operation. So what you do then is, okay, here we have this much head initially, and you continue this test until, let's say, down here. So let's call this H final, and let's call this H0. So your head starts from H0 and goes to H final, and this much is the volume that has flown. But this time we have something slightly different. The difference is now head is variable through the test. If the head is variable, and if I write Darcy's law, which is Q is minus Ki, I am going to actually put the minus in this case because it matters in this one. So Q is volume of water over time makes large Q, the discharge rate, the flow rate. Divide that by area of soil. So that's my flux is equal to minus K times I, and I here is the H over L. Here's my L. So it's going to be H over L. But the question is, at any given time, what you have is so let's say at this level, at any given time, you have H, and over a time of dt, your level changes by dH, and you have to integrate. So if you consider that little time increment, now your volume becomes dH times small a. But because volume happens as head goes down, it's going to be a minus. Divide that by, instead of t, I have now dt times big A is equal to k times, again actually for hydraulic gradient, I'm going to be writing H over L. But actually this implicitly has its minus, so I'm just going to put these pluses because this H, it is lower on the bottom side, so let's not confuse that sign convention. So anyway, from here, if you separate dH together with H, what you end up with, if you take the integrals as well, what you end up with is going to be K is going to be equal to AL over AT ln H0 over H final T. Of course, this T is T final minus T0. So in this way, we can determine lower hydraulic conductivities, but still this presents a problem. So it also, the bottom notes I put for constant head permeability is also valid here. So you have to, in this one, not necessarily upwards flow, but you have to make sure it is saturated and make sure it is more or less steady state. But the problem is but fine soils can change volume with stress. Why does that matter? Well, if volume changes, porosity changes. If porosity changes, that affects hydraulic conductivity. So, in order to uh, address that, what you really need flexible wall permeability or hydraulic conductivity test. So in this one, what you have is your soil in between porous stones and surrounded by, and then connections to those. And then you enclose this in a chamber. So kind of like a triaxial cell, if you are familiar with it. If you aren't, don't worry. In a couple of chapters, maybe next month, we are going to talk about that in detail. But anyway, for now, just know that you have this impermeable membrane. And here basically you have a cell fluid which applies your stress. So this, you have a box, you have a container in which there is fluid, and because you have a rubber impermeable membrane here surrounding the soil which doesn't offer resistance, once you apply fluid pressure on the outside, it cannot go into the soil, but it is applying total stresses. And from top and bottom, you have controllers that can control and measure both water pressures and volume of inflow-outflow. So you can achieve multiple things with this. And you can, for example, apply pressure into the pores to simulate what's happening underground, you can apply, of course, you always have to apply a greater total stress to keep some effective stress on it. But you can basically simulate in situ and while simulating the in situ stresses, now you are able to apply a gradient because you have separate pressure. You can apply separate pressures on top and bottom. Another thing you can achieve is at large gradients because you have a tiny 10 centimeter soil maybe, but you can apply several meters of head difference because you have independent pore pressure control interfaces. So this is the best test you can apply in the laboratory. But then the question is that enough? Because hydraulic conductivity isn't like any mechanical test. In a mechanical test, okay, if you have some part of your soil is weak, the other part is strong, the strong part is still going to carry the loads. But with hydraulic conductivity, first of all, your orders of magnitude can vary greatly. So for example, if you consider sand, 1 millimeter size, a coarse sand, 1 millimeter, 1 squared is 1 centimeter per second. If you consider clay, like 1 micron, and that's 10 to the minus 6. So between sand and clay, there can be a factor of a million in the hydraulic conductivity. So that means with silt it can be 1,000. So what that means is, if you have like little bedding planes, little layers of soil, so don't consider several meters, but now in centimeters, even with silt, clay, silt, sand, clay, etc. Let's call them micro layers. Now, can be present in especially sedimentary deposits. Then, if you have something like this, then imagine if you want to apply flow vertically or horizontally in this. For vertical flow, your flow will still have to go through all these clay layers. But for horizontal flow, if you are trying to just make horizontal flow in this, there is a sand layer, so all of the flow will just prefer to go through the sand layer. The others won't matter because sand is like 1,000 times more conductive than silt, which is 1,000 times more conductive than clay. So everything will be very close to the hydraulic conductivity of the sand. So the vertical permeability can be much smaller than the horizontal permeability. And this is, yeah, here it is vertical versus horizontal. More correctly, it is actually like this, relative to bedding planes. Now here is the problem. When you go and take a sample out of soil, most of the time what you end up doing is you end up getting a subsample from a random layer and in the vertical direction. So most of the time you are underestimating the hydraulic conductivity. So this is one effect. The other effect is K lab is generally smaller than K field, both because of this anisotropy and because of heterogeneities. So what you need to do then is you need pumping tests from the field. May give better results. So there are many different schemes possible, and they are beyond the scope of this course. But for geological engineering students, you are going to have a hydrogeology course next term, I suppose, and I'm sure you will cover them greatly there. So the idea is you drill a borehole, and let's also say here is your groundwater initially. What you do is you pump out Q, and when you pump out Q, you will lower this water table, and you get a drawdown cone that goes asymptotic to your original water table. And then there are many equations, many ways of handling this. One of them being simply drill an observation well as well and observe the water level here. And basically this, I know this looks like a 2D flow problem, but actually you can formulate it into a one-dimensional, you can formulate it with 1D equations if you consider this like a cylinder and the lateral area like your flow area, and the flow is happening in the radial direction like this flow. So again, if you, for example, write actually not volume, Q over A is going to be K dH over D, this time R. Here is your R coordinate. Why? Because flow is happening in that direction as well, and your hydraulic gradient is simply this, because this is the water surface, so at any point on it, the total head is that elevation. So here is your hydraulic gradient then, and then your A becomes, and let's call this H. So your A becomes 2 pi r H, the lateral area of a cylinder through which flow happens. So then what you get is Q ln R2 over R1 becomes pi K, of course this K is KH, because the flow is happening horizontally, H2 square minus H1 square, where these H's and R's are measurements at different points. They can be the borehole, for example, let's call it H2, and this can be H1, the edge of the pumping valve, and so on. So anyway, you can, I'm not, this is not a part of this course, I'm just showing it to give you an idea. There are even more possibilities, especially in the field. So don't worry about this equation. We are not going to ask this in the exams or homeworks. And so this is like pumping at a constant Q. So this is like a constant head. There is also a falling head version, etc. But anyway, this is just an extra bit of information here.